I've written up here on the board the results of some of our previous work. We had characterized the acceleration and this vector b, and we defined our unit vector and calculated its derivative. So I've just got those up there because we're going to be using them in this next step. We have reached my favorite part of this derivation because we are now going to be characterizing the vector v cross b. Why we would care about this vector is not at all clear. That we do, I'm telling you. And it's also not at all clear why I'm going to write it this way, although it should be very clear that I can write it this way. Clearly, v cross b would be an antiderivative of the derivative of v cross b. Okay? So in order to describe v cross b, we're going to take its derivative, and then we're going to untake its derivative to get a different way of describing v cross b. Did I mention that it's not your job to be predicting what I'm going to do or why I'm doing it, but just to follow that I can, in fact, do it, that that's true? This is an excellent example of why it's important to keep that in mind. All right, now, if I were to calculate just this derivative first, and then we'll integrate it. So the derivative of v crossed with b, I can use the product rule for the cross product when I'm taking the derivative. And so I'm going to get the derivative of v crossed with b plus v crossed with the derivative of b. Okay. Well, the derivative of velocity is just acceleration. So this first term is going to be a crossed with b. Plus this second term, well, b was constant. So the derivative of b is 0. So this is going to be v crossed with 0. And of course, that's just the 0 vector. So what I get is just a crossed with b. Okay. So I can say that this derivative here, which is what we're now going to integrate, is a crossed with b. So we're integrating a cross b dt in order to get a new characterization for v crossed with b. All right, clearing some space. Now here's where I'm going to take advantage of the fact that I've previously spent some time characterizing a and characterizing b. So I can say we're going to be integrating a, which was negative gm over r squared u, crossed with b, which was r squared d theta by dt copies of k. That's what we will be integrating. Now notice this is a cross product where in both cases I've got a scalar in front of the vector that I'm crossing. So I can use the property again that I can pull those scalars in front and then just work out the cross product u crossed with k. So we're going to have the integral of this scalar here was negative gm over r squared times this scalar here was r squared d theta by dt. I can see those r squareds are going to cancel, and then I'm using this resulting scalar to scale u crossed with k, and then we'll integrate that with respect to t. Let me just write that a little bit neater. So we've got the integral of negative gm d theta by dt, those are the scalars that didn't cancel, times u crossed with k, and that's what we will be integrating with respect to t. All right, I'm going to leave this up here and then do some side work to calculate u crossed with k. All right, so I'd previously written u in bracket notation, so it was just cosine theta, sine theta, 0. Here I've written it as a sum of some i's and some j's. Okay, doesn't matter how I write it, but I'm going to choose to do it that way. So if I work out u crossed with k, that's simply cosine theta I plus sine theta j, and I'm crossing that with k. Now, the cross product distributes over this vector addition, and I can just write the scalars in front. So this is going to be cosine of theta times I crossed with k plus sine of theta times j crossed with k. And when I'm crossing these unit vectors, remember there's a nifty shortcut. If I just draw I, j, and k in this triangle like so, if I want to do I crossed with k, I can see I'm not following the direction of the arrows. That tells me I'm getting the opposite of the next vector. So this is going to be negative j. And if I do j crossed with k, that's going to be I. So what we get is negative cosine of theta times j plus sine of theta times I. Okay, now I'm going to just rewrite that. Usually we write the i's first and then the j's. So that's sine theta times I minus cosine of theta times j. Now notice, not ready to point that out yet. Never mind. Don't notice anything yet. Okay, so I'm going to just plug that in for my u crossed with k in here. So we're trying to integrate negative gm d theta by dt times this vector, sine theta times I minus cosine theta times j. We're going to integrate that with respect to t. Now, if I combine this negative sign, this d theta by dt, and this vector, sine theta I minus cosine theta j, notice what I get. I'm going to get negative sine theta d theta by dt copies of I. Distributing that negative, it'll become plus cosine of theta d theta by dt j. So I can say these pieces that I've circled combine to give me du by dt. So this integral that we're going to do is just the constant g times m times du by dt. Okay, this is looking like it might be a relatively simple integral. I know that I can factor constants outside, so we're getting gm times the integral of du by dt with respect to t. But I know that when I integrate a derivative, I get the original function back. So I'm going to get gmu plus c. Don't forget, we're doing an indefinite integral. Anytime we do an indefinite integral, there's our constant of integration. Okay, so I'm not just getting gmu, I'm getting gmu plus some constant. And I can actually treat this as an initial value problem because we were trying to characterize, let's see, do we remember what we were trying to characterize? Yes, we were trying to characterize v crossed with b, and I do have an initial condition for that. I have an initial value. The initial value would just be the initial velocity crossed with b. Okay. So I know that that is what I will get at time t equals 0. So I can try to plug in to figure out what this constant of integration c should be. I must refer to my notes for a moment. Yes, okay. So I've been writing everything in terms of i's and j's and k's. So I'm going to just remind us, this is our initial condition, or our initial value. If I write that in terms of i's and j's and k's, remember that my initial velocity, was pointing in the direction of J. Remember, that's how we set up our coordinate system to begin with. Okay. And I know that B, we had a couple of characterizations of B. I've used this more complicated one here, but we also got this as R naught, V naught times K, because we got that by just crossing the initial position with the initial velocity. So I can say this is V naught J crossed with R naught, V naught K. That's going to be, let's pull those scalars in front, so that's going to be R naught, V naught squared copies of J crossed with K. J crossed with K is equal to I. So we're going to get R naught, V naught squared copies of I. Okay, excellent. Now that's what we get when T is equal to 0. Now if I look here, G and M are constants. U is a function of time. I'm going to need to evaluate that at time 0 as well, and then C is a constant that I'm trying to solve for. So let's clear some space. So we're saying this function at time 0 is equal to this. Okay, so R naught, V naught squared I is equal to GM. Let's figure out what the U value is at 0. Now remember, U was just cosine of theta times I plus sine of theta times J. And at time 0, theta was 0. When T equals 0, theta is 0. Why is that? Well, remember we said that our initial position was pointing in the direction of the positive x-axis. So at time 0, our position vector is parallel to the x-axis, pointing in exactly the same direction as I is, so that we're making an angle of 0 with the positive x-axis. So U evaluated at time 0 will be cosine of 0, which is 1, copy of I, plus sine of 0, which is 0, copies of J. So that's just I. So GMU actually becomes GMI, and then plus C. We want to try to solve for C, so of course I'm going to subtract this over. So we get C is R naught, V naught squared times I minus GM times I, and I can factor out that I. That's R naught, V naught squared minus GM, that many copies of I. So we are able to, putting the pieces together, say that we can characterize V crossed with B. Remember, this entire video has been about characterizing V crossed with B. It's not yet clear why we care about characterizing it, but we've had some fun describing it, and we're now able to say that that's equal to GMU plus this specific constant, R naught, V naught squared minus GM copies of I. Wacky fun.